Okay, so you have been working on section 12.3 and you have worked through a good variety of problems. And I want to just do another problem with you. It's one of these problems where you have to reverse the order of integration. We did one like that in our last class, but I'd like to do another one with you. Okay, and so let's just call this an example or a warm-up in this case. So let me give you a moment to copy this example down, okay? Take a moment to copy the example down, and then we'll talk about its solution. Okay, so we have a double integral here. Just change the font. Yeah, we have this double integral. And the integral cannot be integrated if we do dx first, because if we were to do dx first, well, the inner integral would be this integral. So we're integrating with respect to x, and that means we would need to find the antiderivative of the cosine of 2x squared. Now, the antiderivative of the cosine of x is the sine of x. But what's the antiderivative of the cosine of 2x squared? We don't know. It probably doesn't even exist. So this is why they say reverse the order of integration. We cannot evaluate the integral unless we reverse the order of integration. Now, you have x limits. So, like for instance, you have a y. Well, when you see the y, let me just now, all right, so this is x equals y, right? So the bottom limit on the inner integral is y, but it's really x equals y. And the top limit here is x equals square root of 3 pi. See, for double integrals, the inner integral, you have two functions. You always have to find out your region D for your region of integration. But in this problem, they give you the limits, so you can actually construct that region D quite easily. So this region D, whatever it looks like, is bounded below by the function x equals y. So that's a line going at 45 degrees through the origin. And then above by, no, I'm not saying this right. No, because it's dx, because we're integrating with respect to dx first here in the integral, we have here a left function and a right function, right? A left function and a right function. So you're bounding the region on the left side and the right side by these two functions. And then you're limited in the y values. The y values would go between 0 and root 3 over pi. So let's go ahead and draw that figure. So what I have here, part of it got cut off, but it's okay. I can fill it in here. This is now the integral. Well, hold on here. Now, one moment. Right. So this is 0 to root 3 pi. That was the outer integral. And hold on. I got to make sure I'm doing this right. Yeah, we're good. We're good. And then the integral is from y to root 3 pi. So again, the left function is the x equals y, and that's here. X equals y. Region D is bounded on the left by the x equals y function. Now, on the right, the function that bounds region D on the right is x equals the square root of 3 pi. Well, so root 3 pi is a constant, so this is just a vertical line, and there's the vertical line. The limits, are there any questions on that, on region D regarding those inner limits? Are we okay with that? Okay, Yeva's good, wonderful. Wonderful. Noreena's good, okay. All right, very good. All right, so now the y limits go from 0 to root 3 pi. Well, that makes sense because well, first of all, the root 3 pi, I have to draw it a little bigger so I can draw on it. So here's 0 and root, so like, I want to say this the right way. Here's the origin, 0, 0. And here's this point, root 3 pi, root 3 pi. There are, so, I mean, any point in region D, any point, the y coordinate for that point is going to be between y equals 0 and y equals root 3 pi. That necessitates then that the region D is this triangular region. So now that we have that, we're able to rewrite the this double integral. So if we were, and I want to have it, okay, if we had dy dx, if we change the order of integration, I'm going to have this show properly. That's good. Well, now because you're doing the y variable first, you're treating region D like a type 1 region. Okay, and a type 1 region, you go from a function on the bottom to a function on the top, right, for a type 1 region. I mean, that's what you're doing. I'll actually draw another. See? So the bottom function is y equals 0, and the top function is y equals x. Okay, so now when you see x, right, this x means y equals x. And this 0 here means y equals 0. It's your top and bottom function. And then dx would have to go, the x variable would have to go from what? 0 to root 3 pi. And this is much more hopeful for us because if we iterate the integral, okay, if we iterate the integral, which I always do, I mean, you're always doing it, you know, whether you show these iteration symbols or not, you're always doing it, right? But the anti, and I want to just have everything show nicely, so you'll have to, I just want everything to be extremely clear. Okay, so the inner integral, you're integrating with respect to y. So here, you're going to hold x constant. And because of that, we can treat the cosine of 2x squared as a constant. And the antiderivative then of the inner integral would be well, there's several ways to do it. You could do cosine of 2x squared times y and get the antiderivative. But let me show you on the next page how I did it. Okay, but are there any questions on this so far? Who's feeling good so far? Give me a thumbs up if you're good. Okay, Ava's comfortable. Simon, good. And Norina, good. All right, all right. And Aura, very good. I mean, are there any questions? Arian's good, good. Okay, so here's how I did this. How I did the antiderivative. Matthew's good, wonderful, wonderful. So what I did was because this cosine of 2x squared is treated, we're treating x like a constant. So with respect to the inner integral, the cosine of 2x squared is a constant. I can pull that out in front of that integral. I wanted you to show you this because now I could have for that inner integral done, I could have gotten the antiderivative y times the cosine of 2x squared. That would have been fine. But I can also pull that constant function out, and then the antiderivative of 1 is just equal to y. And you know, that's going to get me down. That's going to get me down here. And I'll give you a moment to catch up. But please let me know if you have any questions. Okay, so, well, now here we are. And what are we going to do? Are we going to use substitution or integration by parts? Well, I always like to use try substitution. What I'm trying to say is we kind of know if substitution, I want to say it the right way. If I'm going to consider two integration approaches, uh, for now partial fractions, it's obvious when you have to use that. But between like integration by parts and substitution, I always see, okay, can I do a substitution for this integral? And if I can't, then usually have to use integration by parts. But in this case, a substitution will work fine. So remember now for this third exam, you're going to be showing me your integration work. To get credit for the problem, I need to see your integration work, and I need to see the steps. Okay, that tells me you understand the concepts. So here's a very good example of what to show. Let u equal 2x squared. Okay, so if I write it out a little bit, if u equals 2x squared, du dx equals 4x, and so du is 4x dx, and so 1/4 du equals x dx. Okay, so I mean, I can put in the little details here. How did we get 4x? I mean, you should know that, but hey, I'm not too arrogant to put in details, right? So 2 times 2x, right? That gives you the 4x. So now x dx is 1/4 du. So we know that the cosine of 2x squared is replaced with the cosine of u. And we know that the x dx part is replaced with 1/4 du. And this then gives us this integral. Now, how did we get these new u limits? Okay, how did we get, for instance, 6 pi? Well, 6 pi is equal to 2 times the square root of 3 pi squared. Okay, that's 6 pi. Remember, u is equal to 2x squared. So for our new integral with respect to u, we have to put in our new u limits. And 0, well, that's just 2 times 0 squared. So, x was 0 on the bottom limit. So 2 times 0 squared, 0. And of course, x was root 3 pi on the top limit. So 2 times the root 3 pi squared is 2 times 3 pi, which is 6 pi. One moment, let me see here. Yeah, Yeva's saying could like in the work it would, Yeva, I'm flexible, but I would really appreciate if you went all the way down here, right? Because I mean, I know you can do that in your head, that x dx is 1/4 du, but it would be helpful for me when I look at your work that you put in just that little extra step for me. Okay, all right, you're welcome. You're welcome. So now what we have is we have a new integral with respect to u here, a new integral. And that one we can do. Are there any questions before I go to the next page? Okay. So what I do, I generally, as a rule, like to bring constants outside in front of the integral. And the antiderivative of the cosine of u is the sine of u. And now we put in the 6 pi and the 0, the limits. And the sine of 0 is 0. The sine of 6 pi is 0. Okay, that's 6 pi is, well, 2 pi is 360-degree angle. So 6 pi, yeah, 2 pi is 360-degree angle. So 6 pi means that we, well, let me rephrase it. So let me just rephrase it here. I can do that. That's a little weak here. I think I can do better than that. See, the kind of a mess sometimes when you use all the different features, because every time you use a new feature, you got to worry about a new color and a new font size. But we'll do our best here. Okay, so once around, one rotation is 360 degrees, which is 2 pi, right? So 6 pi here is like, so this is one revolution, right? One revolution. And we know like the sine of 2 pi is 0. Well, if you go do 3 revolutions, that'll get you 6 pi, and that puts you back on the x-axis. And the sine of any angle the sine of 6 pi would therefore be equal to the sine of 0, right? And we know the sine of 0 is 0. So look at this. We did all this work and we got 0. How about that? But there's a lot of cool stuff in the problem, and you know, I hope the details here that I'm showing you is this helping you review your Calculus 2 knowledge. Is it a good review for you? I'm hoping it is. Oh, wonderful. Okay, Yeva, Norina, Angela like it. Wonderful, wonderful. And again, on your exam, your third exam, which is posted tomorrow at 6 o'clock. And I know many of you have scheduled it in Examity already, the first version. You know, you're going to have problems, of course, where you have to compute double integrals, and you know, you have to find you know, volumes, and so you need to come up with limits, and I think for the integration for those problems, you shouldn't need any technology that I can see to do those double integrals. So it's gonna, you know, you're gonna be showing me your integration techniques, and I think the integration is, you know, integration can get very complicated. Like that integration by parts, I'm sure you remember integrals like e to the x times the sine of x, where you had to, like, how many remember do integration by parts twice and then you get the integral back, and then you have to add it to the left side? How many remember that kind of thing in Calculus 2 with integration by parts, that kind of yeah, Lexi remembers it. So it's something you ought to be able to do if you're encountered with it. But from what my knowledge is, I think the integrations for the most part is pretty straightforward, right? So all right, for your exam, and I think it was pretty straightforward for your homework too, right? The integration. I mean, hopefully it was pretty straightforward. So okay, wonderful. Lexi says yes. All right, excellent. All right, well, I'm going to stop the recording here. I'm glad I did this problem. I want to make a few comments about the third exam, so I'm going to stop the recording. Are there any questions here before I stop the recording about this example? Okay, all right, very good.